Welcome back. I'm Muggsy, and today I'm going to explain stoichiometry. Well, congratulations for making it this far. Stoichiometry, to me, is kind of the capstone skill of chemistry. Once you know how to do stoichiometry, you can do pretty much everything else, and it's going to open up the gates to all kinds of interesting things. The downside is stoichiometry is where a lot of students really struggle with chemistry, because in their mind the math gets a lot harder. I would say it doesn't really get harder, it's just there are more steps, so there's more places you can go wrong. So it's important you learn how to do it correctly. I'll totally walk you through step by step how to do stoichiometry problems, and if you've been following my videos up to this point, you should be well equipped to do that. So congratulations for getting here. Now, what is stoichiometry? Stoichiometry basically is just stoichios and metry. Stoichios means elements, and metry means to measure. Just like a meter is a unit of measurement, the metric system is for measuring, geometry is measuring the earth, all that stuff. So all it is measuring chemical equations. Up until now, we've talked about chemical equations in these really abstract terms. Like, I'm going to take hydrochloric acid and I'm going to make water and magnesium chloride. And that's really great. That's useful for understanding what's going on. But in the real world, or in the lab, for example, we can't just take a hydrochloric acid atom and a water atom and stick them together and that sort of thing. We have to actually have quantities we can work with. So like milliliters of liquids and grams of solids and that kind of stuff. So in stoichiometry, we'll actually be using real units of these different molecules. So grams, milliliters, etc. Now previously you might be used to working in moles, and that's great. The whole point of working into moles is to get us to these units like grams, where we can actually measure them out and use them in the lab. So let's get started, and let's start with some review. So here I have a chemical equation. It's an acid-base neutralization. I'm taking hydrochloric acid, reacting it with magnesium hydroxide to make water and magnesium chloride. That's kind of known as a neutralization. You should be able to, at this point, balance this equation. You should be able to determine mole ratios, and let's do those right now. So let's balance this guy. We have one magnesium here in the reactants. We have one in the products. Okay, that's easy. One chlorine in the reactants, two in the products. So let's put a 2 in front there. And now we got to do our H's and O's. These are the ones that are going to be a little bit harder, right? So for hydrogens, we have 2 hydrogens here and 2 hydrogens there for a total of 4 in the reactants. We have 2 in the products for a total of 2. So that's not enough. Let's put a 2 in front there. Now we have 4 in the products, 2 times 2, and we have 4 in the reactants, 2 here and 2 there. Let's check our oxygens. 2 times 1 is 2 in the reactants, 2 times 1 is 2 in the products. So we're balanced, actually. Okay. You should also be able to answer this problem. If I start with, let's say, 10 moles of HCl, you should be able to tell me how many, let's say, moles of magnesium chloride that's going to produce. Question mark, moles of MgCl2. And you do that by using the mole ratio. The mole ratio of hydrochloric acid to MgCl is, hopefully you know this one, 2 to 1, because there's a 2 coefficient in front of the HCl, and there's no coefficient in front of the MgCl, which just means 1. So for every 2 HCl's that we use, we're going to produce 1 magnesium chloride. So let's do this math problem. If I have 10 moles of HCl, and I want to get moles of magnesium chloride, so that's going to go on top. I want to get rid of, obviously, moles of hydrochloric acid. And the ratio of these things, as we said earlier, is 2 to 1. Now let's be careful where we put it. The 2 is HCl and the 1 is magnesium chloride. For every 2 HCl's, there's going to be 1 magnesium chloride produced. And now this just becomes a really simple math problem. 10 times 1 is 10, 10 divided by 2 is 5. Cancel moles of HCl with moles of HCl, and we're left with moles of magnesium chloride. Okay, so that technically is all review. If it isn't, you can look at my video on writing chemical equations, balancing chemical equations, and then also my video on mole ratios. The only thing that's new here is we should be able to say, if I had 10 moles of HCl, instead of how many moles of magnesium chloride are produced, how many, let's say, grams of magnesium chloride are produced? Well, that also should be review. So as we've established, 10 moles of HCl are going to make 5 moles of magnesium chloride. In order to figure out how many grams that is, all we have to do is use the molar mass of magnesium chloride. And if you don't know how to do that, you can look at my molar mass video as well. So we're going to take our 5 moles of magnesium chloride, MgCl2. We want to get rid of magnesium chloride. The thing we're trying to get rid of always goes on bottom. And what we're trying to figure out is grams of magnesium chloride, so that's going to go on top. And again, hopefully by now you've gotten used to, instead of just using units like moles and grams, you're also writing the thing that you're talking about, magnesium chloride, magnesium chloride. That's going to be really useful when we learn stoichiometry in this video. Okay, so now all we need is the relationship between moles of something and grams of something. And as we learned earlier, that's in the molar mass. So let's calculate that now. The molar mass of a compound is just the atomic mass of every element in the compound multiplied by how many of them there are. So in order to find the molar mass of magnesium chloride, we're going to need to look in the periodic table and see the atomic mass of magnesium and chlorine. And when you look in the periodic table, you'll see that magnesium has an atomic mass of 24.3 grams per mole, and chlorine has a molar mass of 35.5 grams per mole. Now remember, there's 2 chlorines in every one compound, in every one molecule of magnesium chloride, so that means we're going to need to multiply that by 2. So in order to get our final molar mass, we would just basically do 24.3 plus 35.5 times 2. And when we do that, we're going to get, what are we going to get? 95.3 is what I'm seeing here. Let me make sure that's right. Yeah, it looks right to me. And the units on that, again, are grams per mole. 95.3 grams per mole. So 95.3 grams goes on top for every 1 mole on bottom. Again, your conversion factor, I say this all the time, should always make sense when you speak it aloud as a sentence. The molar mass of magnesium chloride is 95.3 grams per every 1 mole. Okay, so we just need to take that number now, multiply it by 5 to get our final answer. So if you put that in your calculator, you get 476.5 grams. Which, depending on how your teacher wants you to report values, you might call that 477 grams, up to your particular class. And now, presto, after working in these kind of abstract realms for so long, we now have actual gram values to our chemistry problems. So if I started with 10 moles of HCl, I'm going to produce 475 grams of magnesium chloride, an amount that I can actually measure and predict. And that's what's so cool about stoichiometry, is it opens up the actual world of measurement and allows us to actually do chemistry in the lab. Typically in my classes, students don't do much actual chemistry before they get to stoichiometry. And once they get to stoichiometry, we can do all kinds of labs and stuff because they'll actually know how many grams of their reactants are required or how many grams of their products are going to be produced, and they can actually make some predictions about their chemical reactions. Let's look at another example. Hopefully, you're seeing that these actually aren't that complicated. It's just a bunch of extra steps. All we're doing is the stuff that we've learned up to this point. We're balancing equations, we're using mole ratios, we're calculating molar mass, and we're using conversion factors. So, here's the problem. What if I started with, let's say, 20 grams of K2SO4, potassium sulfate? How much potassium bromide am I going to make, KBr? Specifically, how many grams of KBr are we going to make? Again, the beautiful thing about stoichiometry is we're now working with real-world units, grams. We're not talking about individual atoms, which is impossible to work with in the real world. We're talking about actual measurable units. And hopefully, by now you've recognized that the first thing to do is look at the chemical equation of the reaction and make sure that it's balanced. And in fact, this one isn't. I can see right away I've got 2 potassiums here in my reactants and 1 potassium in my product. So let's go through and balance it. Now my potassiums are balanced, 2 and 2. Let's look at my bromines, 2 bromines here, 2 bromines there, that's good. Let's look at my calciums, 1 in the reactants, 1 in the products. And let's look at my sulfates, 1 in the reactants, 1 in the products. Hey, look at that, it's balanced. All I needed is that little 2 right there. Okay, so let's think of what we're gonna do. The first thing we're gonna need to do here is if we have grams of potassium sulfate, we need to convert that to moles of potassium sulfate. And then once we know our moles of potassium sulfate, we want to know how many moles of KBr that is, potassium bromide. And then finally, once we know our moles of potassium bromide, we need to convert that to grams of potassium bromide. So just a few steps to this problem, but we know how to do all of them. So as long as we kind of work carefully and make sure we're using our conversion factors correctly, should be nice and easy. So let's start. We have 20 grams of potassium sulfate. We want to convert away from grams of potassium sulfate. What we're starting from always goes on the bottom of our conversion factor, so that's easy. What we're trying to get is moles of potassium sulfate. Okay, so how many grams to every 1 mole of potassium sulfate? Well, that would actually be the molar mass. So let's calculate that. In order to get the molar mass of potassium sulfate, we're going to need the molar mass of potassium, which if you look in the periodic table, it's 39.1. And of course, there's 2 potassiums. So that's going to be, what is that, 78.2 grams per mole. Then we're going to look at our sulfur. Sulfur has a molar mass of 32.1. And there's 1 of them, so that's easy, 32.1 grams per mole. And then finally, we've got our oxygens. Oxygen has a molar mass of 16.0. And there are 4 of them. So this is going to be a little bit more complicated. 4 times 6 is 24. 4 times 10 is 40. So that's going to be 64.0 grams per mole. Once we have the molar masses of all the individual parts of our compound, in order to get the molar mass of the overall compound, potassium sulfate, we just need to add them all up. So we've already accounted for the numbers of them, the fact that there's 2 potassiums, 1 sulfur, and 4 oxygens. Now we just need to add them up. This is going to be a 2. This is going to be a 4. This is going to be a 7. And this is going to be a 1. 174.2 grams per mole. That's our molar mass for potassium sulfate. Okay, and again, when you put that into your conversion factor, make sure you get them in the right spot. There are 174.2 grams to every 1 mole and not 174.2 moles to every 1 gram, right? The units of molar mass are always grams per mole. Okay, so 20 times 1 is 20, 20 times 174.2. I don't know what that is. Let's plug it into our calculators. I see 0.115. And what are the units? Well, my conversion factor should always just tell me the units. So grams of potassium sulfate cancel with grams of potassium sulfate and leave me moles of potassium sulfate. Okay, now that I know the moles of potassium sulfate, I want to figure out the moles of potassium bromide. So let's clear up a little space here. So we have 0.115 moles of K2SO4, potassium sulfate. I want to get rid of that, moles of potassium sulfate, because what I'm trying to get is moles of potassium bromide. Basically, if I start with 20 grams of my potassium sulfate, that's equal to 0.115 moles of potassium sulfate. If we have that many moles of potassium sulfate, how many moles of our potassium bromide do we have? Well, we need to use the mole ratio to figure that out. And we can see the mole ratio, I think I might make a mistake here, is 2 to 1. Do you see what I did? Yeah, hopefully you did by now. The mole ratio is for every 1 potassium sulfate, there's 2 kBRs. So what I wrote is for every 2 potassium sulfates, there's 1 kBr. So make sure your numbers are in the correct spot in your conversion factor. For every 1 potassium sulfate, there's 2 moles of kBr. Okay, so all we're gonna do is take our value here, multiply it by 2, and we're gonna get 230? And we're going to cancel moles of potassium sulfate with moles of potassium sulfate, and we're going to be left with moles of potassium bromide, which is good. We're getting closer all the time. For a final step, if we know the moles of potassium bromide, we just need to convert from moles to grams to get our grams of potassium bromide. So let's do that on the bottom here. If we have 0.230 moles of kBr, we got some conversion factor, and we're going to end up with grams of kBr. We want to get rid of moles of kBr, so that's going to go on the bottom. We want to get grams of kBr, so that's going to go on top. And in order to go from moles to grams, we have to use the molar mass. So let's look at kBr. Potassium has a molar mass of 39.1 grams per mole. And bromine has a molar mass of 79.9 grams per mole. So we just add them up. 119 grams per mole. Of course, you could just put those into your calculator, that's fine. So our molar mass is 119 grams of potassium bromide to every 1 mole of potassium bromide. And so if we have 0.23 moles, how many grams is that? Well, moles cancels with moles. 0.230 times 119. I don't know what that is offhand. Let's put it into our calculator. And we get 27.4 grams of potassium bromide. That's our final answer. So, as you can see, I filled up my board with a lot of writing here because these problems have quite a few steps, but none of those individual steps was overly complicated. Let's review again what we did. The original problem was we wanted to know how many grams, if I had 20 grams of potassium sulfate, how many grams of potassium bromide would I make? In order to do that, we had to convert from grams of potassium sulfate to moles of potassium sulfate using the molar mass, which we got by adding up the atomic masses of all the individual elements. That gave us 0.115 moles of potassium sulfate. Now there's a mole ratio of 2 to 1 moles of potassium bromide to moles of potassium sulfate, so we just had to multiply our moles of potassium sulfate by 2 to get our moles of potassium bromide, which were 0.230. Once we had our moles of potassium bromide, it was easy. We just calculated the molar mass of potassium bromide, and we determined that 0.230 moles of potassium bromide is equal to 27.4 grams of potassium bromide. So we started 20 grams here of this. We ended up with a little bit more, 27.4 grams of this. Now you might wonder, why isn't this twice as much? Why isn't this 40 grams? And that's because molar masses are different for different molecules. So even though the ratio here is 1 to 2, a mole of potassium sulfate is actually quite a bit bigger. We calculated to be 174 grams, whereas a mole of potassium bromide was only 119 grams per mole. Now, why is this less than that? Well, because this contains fewer elements than that. Because molar mass is determined by the number of elements and also how big those individual elements are. So 1 mole of hydrogen is going to be really small because hydrogen is a really small element, and a mole of lead is going to be really big because lead is a very heavy, large element. Let's do one more example, and hopefully you'll really understand stoichiometry at that point. Here we have the neutralization of sulfuric acid by aluminum hydroxide to produce water and aluminum sulfate. For this problem, we're going to do basically the same thing we did for the last problem, but instead of starting with the reactants, we're going to start with the products. And this is really applicable to what you might experience in the actual world of chemistry. Let's say I work for a chemical supplier and I need to produce, let's say, 30 grams of aluminum sulfate. Knowing that, and knowing I have unlimited sulfuric acid, how much aluminum hydroxide am I going to need? Okay, let's diagram this problem just like we did the last one. So we're starting with 30 grams of aluminum sulfate. Eventually, we want to get grams of aluminum hydroxide. So the first thing we need to do is, if we know how many grams of this we have, that's not going to tell us how much of this we have, right? We have to use mole ratios to do that. So we're going to convert grams of aluminum sulfate to moles of aluminum sulfate. And then if we know how many moles of aluminum sulfate we have, it'll be easy to figure out our moles of aluminum hydroxide just using the mole ratio. And then finally, once we know our moles of aluminum hydroxide, we can easily figure out the grams of aluminum hydroxide by using the molar mass of aluminum hydroxide. Now there's one more important thing we need to do before we start this problem, and that is check our chemical equation and make sure that it's balanced. And of course, it isn't. So let's balance it right now. Here in my reactants, I have 1 aluminum. In my products, I have 2. So if we put a 2 in front there, we'll balance our aluminums. I'm going to ignore the O's and H's for now. Here in our products, we have 3 sulfurs. Here in our reactants, we have 1, so we're going to need a 3 in front there. So now our aluminums and sulfurs have been balanced. Let's just check our O's and H's. Okay, here in our reactants, our O's. I've got 4 here, and I've got 3 of them. 3 times 4 is 12. And I've got 3 of these, and 2 of them. 3 times 2 is 6. 12 plus 6 is 18. Here in my products, I've got 4 times 3. Okay, that's 12. And then I've got 1. Okay, so that's only 13. So that's not nearly good enough. So I need to balance them. Now I don't really want to mess with my aluminum sulfate here, which accounts for 12 of my oxygens, and I need to get 18. So I'm just going to take 18 and subtract 12 that I know I'm going to get from this aluminum sulfate molecule, and that leaves 6 oxygens that I need to get from my water. So now that's actually pretty easy. I'll just put a 6 in front of my water there, and that'll take care of my oxygens. So let's count them up again. 6 times 1 is 6. 4 times 3 is 12. 6 plus 12 is 18. Oxygens are balanced. Let's check our hydrogens. Here we have 3 times 2 is 6. Here we've got 3 times 2 is 6 for a total of 12. And here we've got 6 times 2, which is 12. So now we're all nice and balanced. Hopefully that's a review for you and you've gotten pretty good at balancing chemical equations at this point. Okay, so now let's just take it step by step. First step is we're going to convert from grams to moles. So we're going to start with 30 grams of Al2SO4 3. And we want to get, let's use pink for this, moles of aluminum sulfate. And we want to get rid of grams of aluminum sulfate. And in order to do that, we're going to need the molar mass of aluminum sulfate. So let's calculate that now. Aluminum, if you look it up in the periodic table, has a molar mass of 27.0 grams per mole. And there are 2 of them in our aluminum sulfate molecule. So we're going to multiply that by 2 to get a total of 54.0 grams per mole. That's my aluminum. Then we got our sulfur. In our aluminum sulfate molecule, there's 3 sulfurs, right? There's 1 here, but there's 3 sulfates, so that accounts for 3 of them. And each individual sulfur has a molar mass of 32.1 grams per mole, if you look it up in the periodic table. So 3 of those are going to be 96.3 grams per mole. And then finally, our oxygens. Man, we have a lot of oxygens here. So if you look up oxygen in the periodic table, it's got a molar mass of 16.0. Over time, you might start to memorize some of these. I don't ask my students to memorize them, but they always just do as a product of working on these problems so much. So if you start to memorize them, that's very cool. I've got a bunch memorized, obviously, because I do this a lot. Okay, 16.0. How many of these oxygens do we have? Well, each sulfate has 4, and there's 3 sulfates in an aluminum sulfate, so 3 times 4 is 12. So this is kind of a massive one. I'm going to use a calculator here. 16 times 12 is 192. Probably should have known that, but whatever. Okay. 54 plus 96.3 plus 192 is equal to 342.3. I'm only going to take this out to 3 significant figures because usually when I do my problems, that's how much I use. Grams per mole. And that looks like that kind of makes sense. Now that we know the molar mass of aluminum sulfate, we can plug it into our conversion factor. There are 342 grams for every 1 mole of aluminum sulfate. And then it just becomes a pretty simple math problem. 30 divided by 342 gives us 0.0877 if I take it out to 3 sig figs. And the units there are moles of aluminum sulfate. Okay, first step done. Let's move on to the next step. Now we need to go from moles of aluminum sulfate to moles of aluminum hydroxide. Let's make a conversion factor. We want to get rid of moles of aluminum sulfate. We want to get moles of aluminum hydroxide. And then here we just need to look at the mole ratio for every, there's no number in front of aluminum sulfate, so that becomes a 1 aluminum sulfate. There are 2 aluminum hydroxides. Make sure you get those numbers in the correct spot. 2 aluminum hydroxides to every 1 aluminum sulfate. Then we just cancel units. Moles of aluminum sulfate cancel with moles of aluminum sulfate, leaving us final units of moles of aluminum hydroxide. And I guess we should do the math as well, right? So 0.0877 times 2 gives us something like 0.175 moles of aluminum hydroxide. And that actually makes sense. This is a bigger number than that. It's twice as much because for every 1 mole of this, we're gonna make 2 of those. Okay, cool. Let's use that now that we've done that conversion to convert moles of aluminum hydroxide to grams of aluminum hydroxide. Last step, we just need to convert moles of aluminum hydroxide to grams of aluminum hydroxide. Let's set that up. We want to get rid of moles. We want to go 2 grams. How do we do that? The molar mass. So let's look it up. Aluminum has a molar mass of 27. Or let me do this someplace else so it's a little bit out of the way. I can do it down here. Aluminum has a molar mass of 27 grams per mole, and there are 1 of them. Oxygen has a molar mass of 16 grams per mole, and in every 1 aluminum hydroxide, there are 3 oxygens. So that's a total of 48 grams per mole. And then finally, hydrogen has a molar mass of 1.01 if we go out to 3 places, grams per mole. And there's also 3 of those, so that's 3.03 grams per mole. So if we do this addition, we end up with .78 grams per mole if I take it out to 3 places. So let's use that. The molar mass of aluminum hydroxide is 78.0 grams to every 1 mole. And now I just have a pretty simple math problem. I take my 0.175 moles of aluminum hydroxide, multiply it by the molar mass of aluminum hydroxide, which is 78, and I get 13.7 grams of aluminum hydroxide for my final product. So if I started with 30 grams of aluminum sulfate, I ended up with 37 grams of aluminum hydroxide. Okay, this last step, I always recommend with my kind of math problems in science, is you should be able to kind of think your way through them and they should make sense. So what is the relationship between 30 and 13? Well, 13's a smaller number. So why would it be that if we started with 30 grams of this, we got less of aluminum hydroxide? Well, there's a couple things going on. Aluminum hydroxide, there's 2 of them to every 1 aluminum sulfate. So you would actually expect that number to be bigger, right? Well, the difference comes in the molar masses. Remember, the molar mass of our aluminum sulfate there was 342 grams per mole. That's pretty big. And the molar mass of our aluminum hydroxide here was a lot smaller, 78 grams per mole. So 30 grams isn't that many moles of aluminum sulfate because each mole of aluminum sulfate is so big, right? It's like 4 times bigger and a little bit more than each mole of aluminum hydroxide. So it kind of makes sense that if we had 30 grams of aluminum sulfate, that's kind of a small number of moles, but we're going to multiply that by 2. But the moles, each individual mole of aluminum hydroxide isn't very big. It's only 78 grams. So it's not going to be a very big final product. It's only going to be 13.7 grams. And remember, once again, we did this problem backwards. So a better way of saying this is if we started with 78 grams of, sorry, not 78, if we started with 13.7 grams of aluminum hydroxide, we're going to end up making 30 grams of aluminum sulfate, because it's going to make a smaller number of moles, but each one of those moles is a much bigger, because aluminum sulfate is such a big molecule compared to aluminum hydroxide, and so we're going to get a fairly large quantity. And that's all you need to know to answer these stoichiometry problems. There's a lot to them. I often see my students take up like half a sheet of paper, sometimes a whole sheet of paper, to do these problems. The secret is be patient, take your time with it, make sure you're not screwing up. You need to write a lot. You'll notice every time I solve one of these problems, I use my whole board, some cases many times over. But all you're doing is really simple math. It's just conversion factors using your balanced chemical equation, using your molar masses that you're calculating for different compounds, and then using the mole ratio between those compounds. That's all there is to stoichiometry problems. So they're not hard, but they are kind of long. So make sure you're being patient and make sure you're writing all your conversion factors out, canceling stuff out that way. And you should get the right answer every time. I'll give you another video with more stoichiometry practice problems on it, but hopefully this is enough to get you started. I'll see you next time.